we present our work GazeNeRF, 3D-Aware gaze redirection with neural radiance fields. Given a face image with its corresponding gaze label, the gaze redirection task is to generate synthetic face images with different gaze directions. In this work, GazeNeRF reformulates the task as 3D-Aware neural volume rendering and disentangles face and eye regions, allowing for the rigid transformation. GazeNeRF employs a two-stream MLP structure that learns the features of the eyes region shown in yellow and faces only region shown in blue. We explicitly apply a 3D rotation matrix to the features of the eyes. Then combine the features from two streams shown in orange to render the whole face. We feed three features to the neural rendering module to render the 2D images. GazeNeRF achieves the best performance on gaze and head pose redirection errors and comparable performance on image quality to the state-of-the-art methods. Here are some results of GazeNeRF. Existing gaze redirection methods formulate this task as a 2D image manipulation problem. They can mainly be categorized into two classes: image warping and synthesizing new images via generative models. Image warping methods cannot model large changes due to the inability to generate new pixels. While 2D generative models can produce high-quality images and allow for large gaze direction changes, they do not take the 3D nature of the task into consideration. This can lead to spatiotemporal or identity inconsistencies, where other latent variables are entangled with the gaze direction. Recently, a NeRF-based head model, GazeNeRF, was proposed to generate face images with efficient control of face pose, identity, expression, and appearance. However, it is incapable of redirecting gazes due to task purposes. In this work, we reformulate gaze redirection as a 3D task and propose GazeNeRF. To endow NeRF architectures with 3D-Aware gaze redirection capabilities, we propose a novel two-stream MLP structure that predicts feature maps for the eyeballs and the rest of the face region separately. The reason for the design is that the physical face and eyes are not a monolithic 3D structure but are composed of two 3D structures: the face without eyes that deforms and the eyes only that rotates when we move our eyes. With the explicit separation of the eyeballs, GazeNeRF rigidly rotates the features of the eye region by the desired 3D rotation matrix, which is computed by the target gaze direction. To train GazeNeRF, we employ four different losses. We first employ the reconstruction loss, which is the L1 distance between generated face image and the reference image. To guarantee we apply the rotation matrix only to eye features, we also penalize the reconstruction loss between the generated images from two streams and the masked reference image. Similarly, we employ the perceptual loss between the generated images and the reference image or masked reference image. The perceptual loss is the L1 distance between the feature maps of two inputs via a classification network. Additionally, we employ functional loss and disentanglement loss, which are inspired by the previous work, STED in GazeNeRF. Please check our paper for more details. We also conduct the cross-dataset evaluation on another three gaze estimation datasets. GazeNeRF achieves the best performance for most evaluation metrics. We analyze GazeNeRF through a number of ablation experiments. Among all ablations, GazeNeRF achieves the best performance in terms of gaze and head pose angular errors by taking advantage of the combination of two-stream MLP structure, applying a rotation matrix to the eyes stream, and using the function loss. We also visually compared our generated images with the ones by previous state-of-the-art methods, STED in GazeNeRF. The blue circled images are generated by STED. They show us TED suffers from the loss of personal identity information. The red circled images are generated by GazeNeRF. Even though GazeNeRF can preserve personal identity, it fails to generate fine-grained eyes. It even shifts gaze direction in some cases. Compared with these two state-of-the-art methods, GazeNeRF generates higher quality face images with the target gaze directions and fine-grained eyes. Here are the animations. They are generated by GazeNeRF with three different settings: changing target gaze labels only, changing head poses only, and changing target gaze labels and head poses at the same time. Thank you for watching.